to talk 20 minutes about the topic which could take 4 hours. So, who is here? My name is Kaplan. I work at CRVT.
Roman Graf from Austrian Institute of Technology.
And so, big disclaimer. So, especially for me, I dabbled in neural networks way back when at the TU Vienna. But it was a very specialized field back then, and only like in 2005, 6, 7, the field exploded. So I sort of missed that part a bit, and a lot of knowledge is there. So that's why I rely on Roman, especially for the machine learning and AI part. But yeah, if you want to know more about this, and we can only cover really a little bit in this short talk, here is the real book. Exactly. That's what you warned me about. Where's the thing for? Here. Here's the book to read. So the goal of this talk is really to get you interested in this topic. And by doing that, to get you interested, basically we want to share what we were able to achieve with classifying Android APKs and our success story, or the current status of it at least. And it's a really interesting field. So, quick start, definition, classical definition of machine learning is you have a computer program that is learning from experience E with respect to some class of tasks T. And then of course you need a performance measure P. And if it improves with experience E. So basically, training. That's what it's all about, yeah? Brief history. This whole thing, especially artificial neural networks, started way back when with the perceptron, and it was pushed back in the 60s, and it was called dumb connectionism. So the whole symbolic AI came to be. Hi, Paul. And it was forgotten a bit, and like backpropagation was invented twice. But then something happened really in the 2000s, that basically with the advantages of GPU power computing, and of course, you know, the new tensor processing units and stuff like that, there were really great successes and progress. So for example, this is the classical picture. That's, you know, success with a probability that this is a MITE image classification, that this is a container ship. So you can see it's pretty good in most cases. And here there is an interesting decision that it's actually classified as cherry, even though this one is bigger. So it's never 100%. That's one big takeaway. It's just, you know, a little bit how our brain works. And we had a great talk about neuroscience recently in this conference. So, brief recap, neuroscience, it was already presented. We have here the cell, the nucleus of the brain cell, the axon, basically output, inputs here, and then of course the reality is way more complex. And the most important thing here is, for our model at least, is this postsynaptic gap or cleft, where, as we heard in the neuroscience talk, chemicals are being passed on, and some are more, you know, the weights. We can model these as weights, and some are inhibitive, and some are enhancing the signal. So, how do we model that? Really, just a recap, or for those who already know it, or for those who want to know more about it, just to give you the brief intro. You have inputs in an artificial neural network. You have weights, the synaptic cleft. You have a summation function, and you have an activation function. This could be a linear or whatever, sigmoid function usually, or ReLU or something. And we model this as the activation function phi of x. Usually that's a sigmoid. We make the sum over the weights and the xi's and put it into the activation function. If that is above a certain threshold, the neuron fires and it passes on the information. If you implement it, this is basically how it would look like in a very simple example, the architecture. And here you could have two outputs. Let's say this is a cat and a dog, and you have 3 pixels in that case to distinguish. It's probably not very useful, but it's good for explaining the architecture. And if you do the inputs here, usually floating point numbers between 0 and 1, multiply by the weights, sum it up and activation function and calculate that path forward. That's what's called forward propagation. As said, inputs are vectors, outputs are again vectors, let's say a classification vector. Backprop does the opposite. It calculates the weights. The weights are usually initialized in a random, hopefully good random initial value, and then the network learns by adjusting the weights over the time with known input, known output. So it's supervised learning. We know the input, we know the output, and we adjust the weights. That's backpropagation. I hope I could summarize it in one sentence now. If you want to know more about that, really read this book. This is really fantastic. And there's lots of YouTube videos, there are lots of tutorials, online courses. Get your feet wet in this field. It's really interesting. It's really fascinating. I'm going to wait a little bit here. Yeah, pictures, okay. There are multiple approaches, of course, with machine learning, and there is one called support vector machines. And we use that initially for a project I did with some students. And I tasked them to re-implement a paper called Dreamin. That's the paper. And basically, it should classify Android APKs based on some feature vectors. I'm going to talk about that in a minute. And the output should be basically be, is this malware, yes or no? Yeah? Or is it benign-ware? Yeah, goodware. And with support vector machines, the approach is different from what I just explained before. The approach is that we have a high-dimensional vector, where we extract some features here. We embed them in a vector space, basically a large bit field. Yeah, it has this feature, yes, no. It sends premium SMSs, yes or no. And that becomes a high-dimensional vector space. And we try to put the dots here in that vector space of the different samples. Let's say we have an example of Android APK which uses very few permissions when you install it, and it's really a regular app that does just something trivial. Let's say a note-taking app. Yeah? And then there's a second Android app which takes all kinds of different permissions and is a game, and it actually doesn't need all those permissions, and it wants to send premium SMSs in addition. That would be a nice, rich feature vector with lots of bits set, and it's probably up here somewhere in the malicious hyperplane area, and we can create a separation hyperplane between the benign and the malicious APKs, the features at least. Yeah? Again, training allows us to create that hyperplane. The nice thing about this approach is, there are some disadvantages. The nice thing about this approach is, if something is in that malicious hyperplane area, you can explain why. You can basically go down the coordinates and say, this actually used premium SMS numbers, or some other, maybe it used a syscall that it didn't have the permissions for. Maybe that hints at a local privilege escalation. And so you can explain to the user. So this is what the Dreamin paper actually did. It was successful, and the task for the students was to do the same, but improve it. Let's briefly talk about the feature extraction, because that's one of the really important parts. APKs are basically zip files with some extra files in there, manifest, MF, and meta-inf directory. There you have the lib, you have the DEX code. I'm sure there are some Android experts here in this area, so I'm not going to explain all the details because you know it better. But basically you can take these and you can decompile the DEX code, get the syscalls which are being used. That's one feature set. And you take the permissions, that's another feature set. So we basically extract those features. We think about what would be a good indicator of maliciousness. Thank you. And we try to create that vector space. So here is the proposed feature set For example, requests to hardware components, GPS, camera, all these things. Maybe a game needs that, maybe not. Maybe a note-taking app does not need the camera. Yeah. Then requested permissions, for example, send SMSs to premium SMS numbers, etc., etc. You can read. And so the feature set of the original Debian paper was like this. We had way more features. We tried to play around with more features and to detect more. The lesson is this is sometimes useful, sometimes not. It's really a balance here. So that's an interesting thing. Yeah? The interesting result is given enough RAM for an SVM algorithm, you get pretty interesting true positive rates and pretty low false positive rates. So we were in the range of 60 till 97% true positive rate, depending on some parameters and the amount of data we put in. Yes, I forgot one important thing. You take the data, you split it, let's say 80-20 or 90-10. 80 is the training set, 20 is the test set. Yeah. Yes, and you train it with the training set, you create the hyperplane, and then basically you test it with the test set. How good was your training? You tweak parameters of the machine learning algorithm, you do it again and again and again and again. So interesting. At the same time, a team from Singapore did the same. It tried to improve that, achieve the same. We synced a bit. The problem that we had, and that's where you come in, is with this high-dimensional vector space, if you're not careful about the feature sets, and you want to basically have all the features, right? That would be cool, but you run out of RAM. Like we maxed out at 200 gigs, and that's sort of what the server gave us, and we would have taken more, but it was too expensive. So the other approach is, as we explained, artificial neural networks, and you had some really good success with that. Yeah.
Thanks. I will briefly present our results for our neural network model. Here you see some examples of our features. It's extracted from this Debian paper, and there are different malware families, and actually features are just strings of sentences. And on this overview, we demonstrate that we will have different situation awareness systems, and in each system we will train our own model, because we noticed that APKs are very different, and it depends on time and so on. So we need to train different data sets. And so we extract data for each data set, features, and we store them and train our model. And additionally, we also want to apply some expert system rules, because sometimes you can immediately say if it's malware or not from different sources as our neural network. It would increase speed and facilitate calculations. And the result of our calculation, we provide in a planned APK feed that should be publicly accessible, and then distribute between interested people. Here, for training of our neural network, we applied word embedding method. It's an established method for this case, and it's simply that we take our text and we should convert it to numbers. Problem is that neural networks cannot work with text, so we need numbers. Then we just take our sentence, like for instance, Hack.lu is very interesting and very helpful, and put it in array and assign to each word a number. So for instance, the word very comes 2 times and has index 3. Then this index we convert in one hot vector. For instance, for word interesting, we have 0001000 for this sentence. And word embeddings can be applied for frequency. This means counting of words, or for prediction. In our case, we use it for frequency count. Then we proceed and We define number of our embedding vectors. So how big is it? In this case, it's 6. The size is 6. And for each file, we create a list of such embedding vectors. So we have a data set. With this data set, we can start our training. Also, we split our data in test, validation, and training sets, as it usually will be done. Here is briefly our workflow. So we extract features, look if already this feature exists in our model or not. If not, then we train, or otherwise we just ask our model. Additionally, we proceed with rule engine. This is a sample of our rules. I will not go deeper now because we don't have enough time. But first rule is our neural network input, and other rules can be completely different depending on time or who has produced this APK and so on. And then it will be automatically take conclusion. We will take conclusion if it's malware or benign sample. In this picture, you see that we apply different parameters that we can change, like learning rate, vector length, embedded vector length, then validation accuracy, training accuracy. And on the right side of this table, you see our example results, like true positive, false negative, how good was working our trained model. And here is a small picture about the training, that our error should reduce during the iterations and our accuracy increase. And you can see below that we used different layers. We flattened our input, then we should we used a dense layer with sigmoid activation function. And on this last picture for our model, you see operating relative operating characteristic plot. It demonstrates how well our model learned. The perfect classification point is on the upper left side. It demonstrates the best results, the best theoretical results, and red line divides good results from bad results. As you can see, our blue points all are in the near of perfect classification point, and in comments you see different parameters we applied for particular training. And I will pass it again to Aaron.
Thank you. So yes, so the idea, how much time do we still have actually? That's good.
About a minute.
Oh, that's not good. Okay. So the takeaway point of this is, I think for the IT security community, usually when I was tempted to make a slide like blockchain, IoT, machine learning, yeah, and everyone would go like, oh, yeah, buzzword bullshit bingo. But I think if you take a look at that, at especially the IT security community, if you take a look at some parts of machine learning, you can do quite something. I'm pretty convinced of that. Of course, it's never easy. It's never like, out of the box. It takes tweaking of parameters. You have to do ROC curves and see what is really working and what not. But I think it's a skill that we should all dig into a bit. It can be a lot of fun. The libraries are really simple, like Keras and TensorFlow and so on. They are accessible for us. They're not like, we have to learn a new assembly language or something like that. It's, that's for some, that's easier. But anyway, there's a lot there already. There are lots of public papers on that on archive.org. And we can sort of have a situation where, let's say, a reverse engineer would see something. I was dreaming about that and talking with Thijs about that. If a reverse engineer can see something, and this code looks ugly, and it looks like it could have potentially so many vulnerabilities in there, maybe we can do some kind of scoring at least. So the system, the machine learning system, will be just like a friend, an expert, helping you and saying, "Hey, this looks like in masses of data. This one looks like it's interesting. Take a look at this one because it looks like crappy PHP code or so." Yeah. So I think we can do that. Similar to when a doctor looks at an X-ray, he's trained. His brain is trained for detecting the cancer. The same success or higher success rates were achievable with deep learning. So, of course, there is one big difference. Like the cancer cell doesn't try to maliciously, with intelligence, try to circumvent any machine learning techniques that we invent to detect it. Our adversaries actually do. So that will not change, of course. We cannot outsmart that, but we can scale up a bit, and I think that's pretty interesting. So here is the GitHub repo. Oops, again. Here's the GitHub repo for the machine learning part, and our email addresses. And I hope we're finished in time. Yeah.
Time enough for a few questions, if anyone has one. All right. If not, let's give them a hand.
There's one.
Well, we have one.
Oh.
Sorry. I would like to know if you how was the proportion that you had between clean files and malware files, or if you were just boosting with your malware files. So
that's a very good question. So we had to make some base assumptions. So we got actually the already classified files from AV vendor. Then we added the F-Droid APK files where you have to submit the source code. So the assumption was that F-Droid files are clean, which I think, well, at least if you're a malware developer and you want to open source your software, you might be okay with submitting it to F-Droid, but usually you don't want that. And of course, it doesn't catch some, specific malwares which will download malware code dynamically. That's not detected. It's static analysis. So you're right. There are lots of assumptions in there. It was one assumption is like what the AV vendor would classify as good and as bad. So we just took that, and it was roughly 50-50. Yeah. Mm-hmm.
Thank you.
One there.
Hello. That's quite a similar question. Just imagine you remove things APK is not detected as malware from your set, and then try some files in your classifier. Let's say you remove Facebook from the training set. How would this kind of file be classified? So that's quite similar. It's about what do you consider as malware?
Yeah. We just had to make some base assumptions. What the input files were the APK file, and basically it was in a folder. Goodware, malware, yeah, very simple. Actually, there was a third one, which is adware, and we pretty much ignored that, yeah. We just overtook that assumption in order to do the training. Of course, if you have a different concept of malware than me, of course, I might have mistrained it for you.
Yeah, we also provide some explanation why we decide that it's malware, because we have our features added to this result, and you can decide by yourself if it's malware for you or not.
Mm-hmm. Yeah.
If you were an attacker, how would you avoid detection by these methods?
One example, as I said, sorry?
Yeah.
So trying to answer that, yes, don't be below the radar as long as possible as an attacker. Second thing is, in this case, we didn't do dynamic analysis. So just download something that's dynamically and then execute it. Voila. Yeah. That's the limit of the system. Yeah.
All right. That's the limit of the time.
Oh.
Thank you very much.
Thank you.
Thank you.